Before you start the next lesson, what I'd like you to do is actually start this activity. It's not in your booklet, so make sure you come see me and get a copy, because we're going to introduce the idea of completing the squares not algebraically, but actually using algebra tiles. So if you're in class and doing this, that's great. Then we can actually use the real algebra tiles. If you're at home, you are going to want to be on a computer, not on your phone, okay, on an actual computer. And you're going to want to go to the website that's listed there. So the Glencoe sites, common assets, mathematics, etc., so that you can actually use some virtual algebra tiles. So the idea is we want to complete the square. So again, this isn't eventually how we're going to be doing it. We're going to be doing this algebraically, but to introduce the idea, we're going to be talking about the algebra tiles. So why do we talk about completing the square? Well, it actually allows us to convert between standard form or general form into vertex form, which is our form that we've been learning about lately. So activity 1 asks you to model x squared plus 6x using algebra tiles. So I'm just going to switch over onto my algebra tiles and I'm going to model that. So I want x squared plus 6 x's. But I don't want them just anywhere. Okay, that is technically representing it. What I'd like you to do is I want you to try to make a square using this. So for our modeling x squared plus 6x, you could draw it the way that I've got it laid out on the screen. But then we are going to try and arrange it in a square. So this is our part 1, just representing x squared plus 6x. But then I need to actually try and position these. Now this is the tricky part when it comes to using a technology-based algebra tile, is that they're a little bit more touchy in terms of movement. If I can drag it. There we go. Now, if I keep building this way, my problem becomes that I'm actually not building a square. So I need to start building in the opposite direction as well. Let's see, is that a square? And then not quite. That is not really. So again, super touchy. So I need to rotate all of these pieces and build a square with them. Okay, so it's starting to look like a square because I do have the same dimensions. So vertically, I've got x plus 3, and then horizontally I have x plus 3. But this isn't technically a square yet because I've got this whole empty space here. And we see that kind of showing up when we mention that your arrangement may have a hole. So that bottom corner isn't accounted for. So how many ones tiles would you need to actually fill that hole? So we go in here and we start moving 1 tiles in there until we fill it. So again, they kind of expand when I drop them, so it's hard to align them right away. Not filled yet after 3. Now there's going to be some discrepancy on these things fitting together just because of my rotating, and I think I've got some tiles slightly overlapping, which is the only downfall of using this program. Touchiness and inaccuracy, whereas if you were using the real algebra tiles, you'd be able to physically just abut 1 tile next to the other. So we've got all those, and how many ones tiles did it take to fill that hole? Well, it took 9. So when I go back to my activity, I'm going to be answering these questions. So then write the expression of your square tell me just what tiles did you use, factor your expression. When we talk about factoring, remember, it's like looking at the dimensions of your rectangle with algebra tiles. So in this case, again, if we look at it, my dimensions haven't changed. I just filled in that hole to make sure it was actually a true square. So that this dimension here is x. Each one of these is 1. So I've got x plus 1. Now this goes back to the definition of what algebra tiles are. So when we talk about this being x squared, it's because it's x by x. And those are its dimensions. And to find the area, that's what its name is. Here we've got 1 by x, and that's why it's just called x, because 1 times x is x. Down here, these little guys are 1 by 1. So if you're having a hard time seeing what actually is the dimensions of this scenario, you can use your tiles to kind of try and identify it. So if I take a tile along here, that defines my x dimension. To define these ones, I'm not going to use an x tile. I'm actually going to use a 1 to describe it. And so it takes 3 1s. I'm not going to be picky about how they're arranged to describe that dimension. Doing the same thing over here, vertically, I've got x, but I'm not done. I need to account for what's below it. So 1, 1, 1 again, and that defines that dimension. So now I've got x plus 3 and x plus 3, and those are actually my factors. X plus 3 times x plus 3, well, those are two exactly the same, which is why it's a square, because we've got equal sides. So when I go to talk about my factored expression, it's going to be a perfect square. So when you move on to activity 2, you're going to be doing the same sort of idea, except now we're actually going to be writing both pieces. So the expression written as a square. So the left-hand side being our given trinomial, and you're going to fill in the hole to figure out how many would make it a perfect square. You're going to tell me how many that was, and then you're going to fill in not only the trinomial but also the factored version, giving me the dimensions of that square. Then you're going to look for patterns showing up given this equation. Okay, so talking about D compared to B, so B being the middle term, D being your constant defining your perfect square, and then C compared to D, so C being your constant term and D being the constant in that binomial of the factor. Okay, so then there's a couple more to practice with, working with. Find the number that completes it. What I'd also like you to do is also write the factored version. This is not the end of completing the square, but this gives you a good foundation in order to be able to do it algebraically. So finish this activity before you move on.